This is the block diagram for a double sideband suppressed carrier amplitude modulation system. Double sideband suppressed carrier amplitude modulation. It is created with the block diagram. This is the block diagram. Very simple block diagram. We have the message signal, or the modulating signal, x of t, applied to one input of a device called a mixer. Sometimes it's called a frequency mixer. It's simply a multiplier. And the second input is the carrier signal, a particular amplitude cosine 2 pi times the carrier frequency fc times t. The mixer multiplies these two signals together and produces the output, a double sideband suppressed carrier amplitude modulated signal. I'll just use the subscript double sideband to keep things simpler. So we can write the time domain equation for this time signal. Phi double sideband as a function of time is simply equal to x of t times multiplied with the carrier AC times cosine 2 pi f sub c t. To illustrate the modulated signal, let's consider a specific message signal. Let's take a sine wave at 4 Hertz and add to that a sine wave at 6 Hertz. And then I took the sum of these two sine waves and normalized it so that the value fell between -1 and +1. I chose these values because I liked the result when I printed out the picture. The carrier signal is a cosine with an amplitude of 1 and a frequency of 40 Hertz. I chose the carrier frequency of 40 Hertz because I liked the result in the picture. In producing the double sideband AM signal, we are multiplying the message signal times the carrier. And you'll notice that in this multiplication, we have the message signal times the amplitude of the carrier stands in the place of the amplitude of the carrier signal. So we are modulating the amplitude of the carrier signal, thus it's called amplitude modulation, and we are modulating the amplitude as directed by the message signal. In order to sketch the double sideband modulated signal, we first need to sketch in the message signal x of t, and then the reflection of x of t around the 0 axis. That would be minus x of t. So the thin blue trace and the thin black trace form the envelope for the modulated carrier signal, and the amplitude of the modulated carrier signal will fit inside this envelope. This diagram clearly illustrates the amplitude modulation of the carrier signal. We can see from the thin blue lines they form an envelope for the high frequency carrier signal, and the amplitude of the carrier signal is directly controlled by the value of the message signal. Also notice that when the message signal crosses from positive to negative, that causes a 180-degree phase shift in the carrier signal.